Thank you all for being here and thanks for the invitations. My pleasure here to talk about this project about model-based smoothing for near-monotone functions. I'm gonna present two approaches and then eventually show I just presented like one unifying method in the end. Yeah, like Spectre already introduced, this is a project I started like years ago when I was a PhD student in University of Toronto. And then in the middle of the project, I started my postdoc and then got distracted by various projects simultaneously. So it's kind of delayed the progress a little bit. So right now I'm still presenting like work in progress, some preliminary result. Hopefully now since I'm really picking up this project and trying to speeding up. So if you are interested, hopefully there will be like a preprint version soon. So today, because the format of the workshop, I won't focus that much of technical details, but I will just hopefully focus on ideas that could be appreciated by both mathematicians and statisticians. And I think it's a bit like a novel attempt of mine, so could be a bit risky if it gets a bit even more confusing. If that's the case, I'm super sorry.
We'll stop.
Okay, so I'd like to start with one of the motivating questions behind this project. So in air quality health index computations, we try to kind of come up with a tool that could be used across Canada to inform public about how health risk associated with various type of air pollutions. And this index particularly looks at exposure to major pollutants like PM2.5, NO2, O3, and how they related to the change of risk of mortality and morbidity. So this relationship is known to be smooth. And of course, if everything works out reasonably, then we expect something near monotone, like near increasing, right? So, and also based on existing study in epidemiology, we know the shape of the curve in most of the case should be close to square root-like shape, but it's not 100% perfect. We're allowing some deviations from this. So this is a smoothing problem we are dealing with because we want to learn the unknown curve from a bunch of data. And it's just compared to the traditional smoothing, we have a little bit more information than usual. Like we have some information about the shape, and also often case we know a little bit about how the curve behaves at certain important reference point. But let's just again revisit the most classic smoothing settings, where you have a bunch of yi response variables. They are associated to a variable of interest xi. You can think of them being the exposure to pollutant. And then there's a linear relationship described by this unknown function f. You observe this response with certain noise epsilon, which we assume to be IID normal, just the most classic setup. So we have scatter plot like the one on the right. You see a bunch of points, and I'm also showing you the true curve used to generate these points, which is this blue dashed line. And we want to learn this function f from those points, and we know it should be smooth, almost close to monotone, and with some shape idea. But before we answer any of the questions, let's unify the term a little bit. What does smooth mean? So since we have both mathematicians and statisticians here in the room, I think in my understanding, this term has a slight different implications in the two fields. So mathematicians, they talk about smoothness when they talk about the property of the curve, like how many times the curve is differentiable, continuously differentiable. But in statistics, at least most statisticians talk about smoothness as a way that implicitly linked to correlations and how much pooling you can do with neighboring points. So if you say the curve is very smooth in a statistical sense, you expect to have like very stronger correlations with the nearby values. So you can learn more about the curve at this point, just looking at the points near it. And if the smoothness is low, then you expect to see more wiggliness. So learning the neighbors won't help you that much about learning the value of yourself. And one way statisticians commonly use to describe this wiggliness is just looking at this integrated square second derivative. So if this thing is larger, you expect the curve to be like more wiggly. So you can learn less from the neighbors. And these equations, I believe many of you have seen it several times throughout the workshop, as the most classic way smoothing problem is viewed as a statistical problem. So we are trying to reach an optimal like trade-off between the fidelity to the data and the fidelity to the smoothness. So the first term here, the sum of squares, eventually is saying like how much the curve you fit is close to the actual observations, and that's the fitness. And second part here, this integrated second derivative is showing you how much non-smoothness your fitted curve behaves. So this penalty terms, you can really view it as like a norm in a sense. It's like looking at the L2 norm of some function of L apply on your function. And in this case, this classic setting L is just the second order differential. So it was back in 1972 when Griswaba first established this relationship of this classical settings, which is also sometimes referred as phase smoothing spline, because the solution to this, if you optimize this objective function with respect to F, you get the cubic spline. It's actually the posterior mean, which is like a smooth result from a model-based approach if you assign a distribution on your unknown curve, which we call prior. Okay, so this prior is a Gaussian process. It's a Gaussian process called integrated linear process of second order, short name IWP2. And eventually, what does this process define is those function F, if you apply L, the second order derivative on F, you get something that equal in distribution to sigma scaled by psi x, which is the standard Gaussian white noise process. And if you want to make it exactly equivalent to the original objective function, you set this smoothing parameter sigma, which is now a standard deviation to 1 over square root of lambda. Then in the limit, simplifying a lot of assumptions, the posterior mean, like the expected value of F given your data from this mechanism is gonna exactly give you the smoothing spline estimate. And but this gives us also a new way to understand what smoothing is doing overall. We are kind of pushing our function to a certain space, and that space is defined by the null space of your differential operator L. And in our case here is linear functions, because those are not penalized. So if you have a linear function, the second derivative is 0, so it won't really have anything in the penalty terms. So this kind of is saying the type of perfect functions our smoother is looking for. So smoothness in this setting is refers to how much you deviate from a linear behavior. If you're really close to being linear, like fitting linear regressions, you won't have any penalty in the second term. And I like to really think about this now in the model-based way when we assign a distribution on the unknown function F, because that way I think it is clear, at least to me, smoothing is nothing more than just a shrinkage problem for a function. So you are essentially, through choosing a distribution on F, you are pushing it or shrink it toward a choice of the base model, which is a set of simpler functions you believe as like the perfect smooth function space. The example is if you use IWP2, you are pushing your function, you are shrinking it toward the base model of linear functions. That's the spine of 1x. So this is really chosen by a choice of the L differential operator. So I like to think about this L as the direction of your shrinkage. So when you choose a differential operator that used to define this prior, this distribution on your function, you choose the direction where I want to shrink it toward. How much I shrink it toward actually depends on the sigma parameter, which I like to interpret as the strand of the strength of the shrinkage. Okay, so this is still a smoothing parameter, but it's now also interpreted as a standard deviation of the functions, how much variability it has. So if you make sigma close to 0, remember the relationship we had 1 over square root of lambda. We are pushing lambda to a really large value and increase the penalty. So there's a stronger penalty pushing the function to the base model. How do we choose the level of shrinkage that is appropriate to our data? There have been so many efforts throughout the workshop. Cross-validations, I think in the first day of the workshop, Tom's already talked about it, which look at this criterion from a predictive perspective, I would say. And if you are more used to the statistical setting, like myself, I like to really think about, because we have this model on the function f, so we can do integration and integrate out the terms that are unknown, that are with the prior distribution. So we end up having an objective function that is just describing the level of evidence supported for the data for each value of sigma. So that quantity in statistics called marginal likelihood. And I like to think about when you maximize this objective function, you are doing empirical phase. So you are optimizing a prior on your function f. And you can also be Foley based to compute a distribution of these unknown smoothing parameter sigma given your data. And this is the default approach we're going to take as the rest of the talk. But let's first see how the traditional IWP approach works in the simulated data. And now let's make this setting a little bit more like what we have in epidemiology. We know the function derivative at reference point 10 exactly, let's assume. So I'm basically giving the true value of the derivative to my model as part of the prior. So reduce its level of difficulty in the inference slightly. This is what I got as the posterior. So for the function f. So this red curve is the smooth result. That's the posterior mean, okay? So you can think of that is the natural analogy of the smoothing spline estimate. And then the shaded regions are the posterior credible intervals. Those are the uncertainty bound, which come up naturally as a byproduct. We have this model-based setup. So if you take a look at this picture, you see most of the times, I would say from 0 to 80, the smoother is doing a good job capturing like the true function. The uncertainty band is reasonable. And if you look at this part where data is scarce, you see the interval becomes more wildly behaved. So that's because if you just look at the estimated level of smoothness, so that, I mean, if you look at this posterior of your sigma, you don't need to worry about what is a posterior if you don't know it. Just remember where this peak is basically where the data is suggesting the right amount of sigma for us. So here it's estimated around like a bit over 1, which actually is a large number. So it's saying there's a large level of non-smoothness. By that, it means a large level of deviation from linear behavior. And that is not unexpected because for square root functions, like this near region behavior is quite fastly changing. So it won't look so linear. So the model won't estimate the sigma that is too small. So when the data becomes scarce, there's a lot of uncertainty. But think about the original question that motivates us to do smoothings. Maybe the space of linear function is not the right direction to shrink toward. And by that, I mean, if we think about AQHI, the health index problems, we know mortality risk as a function of pollutant concentration should be not only near monotone, but also expect to behave a little bit like square root. So we know the derivative is changing a bit faster near the origin. And maybe those are information we should let the model know before it gives us the posterior. So can we shrink instead of to the space of linear function, but to a space defined by some monotone function mx, where mx is my choice of preference, like square root. So one very intuitive approach is to simply transform your variable. Basically, if we define x star to be m, your choice of monotone function apply on the original scale, and then you define fx to be this composition of f tilde on x star, then if you further assume f tilde follows IWP2, that means you are penalizing f tilde toward the linear space, but the argument of f tilde is x star, so now you are penalizing f toward the space of defined by or induced by mx. So because this approach is like so conceptually simple, you just transform the variable and then apply IWP2, so we call it the transform IWP2, TIWP. Okay, so let's see what it looks like. This is the same problem as applying the intuitive approach, the TIWP2. You see immediately that the fitted curve looks much more like a square root behaved functions. And as a result, if you take a look at the estimated sigma level, it's much smaller, meaning there's much smaller deviation from the base model of square root behaved functions. So as a result, you also see that the confidence band becomes much narrower, even in this part when you don't have that much of data. Okay. But is that the only approach can deal with this? Definitely no. We can also define a new operator, L. Recall that when we first introduced this model-based approach, we look at Gaussian process, like distribution of function defined through this simple ordinary differential equation. And that construction is shrinking function toward the null space of L, which we call base model. So if we choose a L that no longer looks like just the second order differential, but second order differential subtract alpha x multiply the first order differential. So here alpha x is any square integrable function. Then if you compute what the null space looks like, which the base model looks like, is the span of one of this type and this type of functions. If you call it M, then it's easy to see alpha there. When you started in your construction, it's just the relative curvature. And it was back in 1997 when Ramsey first proved that for almost any smooth, by smooth now I mean continuously differentiable monotone functions can be written in this format, okay, as one solution to certain choice of alpha x defined equations. So now we are making it a little bit more flexible by changing the right-hand side here to be a scaled Gaussian white noise. So basically we are saying we expect to see the function behave like something in the space, but there's some level of deviation specified through this right-hand side. So it's called monotone induced GP, so we just short name it MGP, okay? Let's see what it looks like now. Fitting this model to the data, you see it's a little bit like the TIWP2 case. The fitted curve mostly resemble a square root shaped function. Still captures well the true function in most of the regions. In the very right region where data is scarce, the interval compared to what you originally saw in the IWP2 case is much narrower, but a bit wider compared to the last figure when you use TIWP2. Okay, and similarly, if you look at the estimated smoothness, it's not as large in the first figure, but a bit larger than the second figure using TIWP2. So now, just to make it easier to compare, let's put everything together here in one picture. You see how this red region change as you move to different model. The top one is original IWP. It is really wide in terms of the region. And this one is TIWP2, it's really narrow, and the MGP is kind of in the middle. So you may wonder, is this kind of thing that happens just by chance? Is this like a coincidence particular for this simulated data set? Like, or is something, there's like a more subtle reason behind it for this difference in the level of uncertainty? And turns out that it's not a coincidence. We can actually unify the two approach introduced just into one single framework. Specifically, we can see that TIWP2 is like a special case of the MGP model. And in this proposition, we show that if you have a f function that follows TIWP, generated by some monotone function m, and then you can rewrite this distribution. So you can basically say this function must also satisfy this equation. So if you apply L on the functions, then it equals to sigma x multiplied with cosine x. So the surprising part is this L is exactly the L operator used to define MGP. And what is sigma x? It's just the original sigma parameter in TIWP multiplied by this factor, which is the derivative of x to the power of certain degree. So basically, it's saying TIWP is like a time varying MGP with changing penalty over time. So what does this mean in practice? Well, if we think of one example of the square root functions, then the derivative of the square root function is 1 divided by 2 times square root of x. So looking at the previous factor we have, when x is really large, that means sigma x is really close to 0. And recall that sigma is interpreted as allowable deviation from the base model. So basically what it's saying is when x is large, there's no deviation allowed in your model. You must trust your base model because that is exactly describing the functions when x is large. And that is a huge assumption we must be aware of. So there's another way to kind of see why this is important. It's through this predictive uncertainty perspective. So let's assume we know the function exactly up to a reference point u. And we want to predict what the function is going to look like h units ahead. So we want to know how much uncertainty we have for this h unit prediction. So the most natural quantity from statistics is just looking at the standard deviation of your function's predicted value given the history of this entire curve. So this quantity is sometimes called h unit predictive standard deviation, PSD. And if you work out the math, this will be just a scaled version of the original smoothing parameter sigma, but it is now comparable across different models. Because sigma there, the original sigma, even though you can interpret it as like a deviation from the base model, but the base model are different across models, right? So how do you compare the value of it? It's not as interpretable nor comparable, but this version, the sigma h, because it just describes the uncertainty in your prediction. So that's something you can compare across models. But why it is important is if we look at this quantity and compute the limit as x goes to infinity, you get very different results for the two approach. In the first approach, when you use MGP, and if we, for now, just look at a particular class of mx defined by this relative curvature, it's actually correspond to the Box-Cox transformation in statistics, then the limit of PSD actually converges to this quantity, and it's actually just the PSD of a second order IWP. So that is basically saying for MGP, if you are evaluating the functions at very right tail, the level of uncertainty associated with your prediction is the same as a regular IWP model. But what happens when you use TIWP2? It actually converges to 0. Okay, so that's something quite important because it's basically saying if you are evaluating a large value and you are given the history of the function up to these values, then you have no uncertainty about the prediction. So basically, you know the functions deterministically just based on the history. And I think this is an obvious way of saying how much assumption we are actually making. Okay, so a bit almost the last slide. I will try to link the topic a little bit to the one of the theme of the workshop, splines. So we know that Gaussian process is often slow in computations. I think Patrick Jamie in yesterday's talk already gave one particular example because we have those dense matrices eventually. So here n is the sample size, the number of data points. It grows up quadratically in memory and cubically in runtime. So it becomes infeasible when n is large. So people like yesterday's talk have trying many approach like Gaussian Markov random field approximation, blah, 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 to make these things simpler. But I'm just trying to say that for the model we presented here, it's not so much of a problem because this differential equation constructions gives us a nice property of the Markovian property of the function. So if you augment the function together with all of its derivatives. So here P, I'm assuming that's the order of your differential operator. Then this thing is Markovian, meaning the precision matrix of this vector is gonna have a sparse structure even without approximation. But if you are interested in evaluating in a very dense grid, maybe you are not 100% satisfied even with this sparse precision structure. You could also do finite element approximations to write this F into a basis expansions with splines. So that means you are replacing F with F tilde, which has like this basis expansion form. And you can work out math just like a regular, how you handle regular ordinary differential equations with finite element approximations. You make sure, in a very intuitive way, your approximations is quite close in distribution to the true functions after you apply L to it. So either way, it will give you a very efficient computation. So I think I'm running out of time, but just showing a very preliminary result. When you try MJP to the air pollution data, this is credit to Gaussian from University of Western Ontario. You see that the result looks reasonable. I don't have time to explain why, but you see that for certain type of mobility, you have more close to square root behavior. For certain type, it is a little bit more deviated. So this is all reflected in the uncertainty band. Okay, so very quick summary. In this talk, presented two approach for model-based smoothing of a function that is near monotone with certain prior information about the shape. And then we actually unified the two approach into a single approach. And because it is model-based, so it is easy to incorporate all those information we have about function's behavior or its shape. Which one to use depends on how much you trust your base model. And for me, because I think the reason we do smoothing rather than parametric regression is because we have uncertainty about its shape. So I'm a little bit biased for the MJP approach. And the preliminary result provided by Gaussian, I think, all shows the promises of the MJP approach in real data. So quick acknowledgement to all the collaborators involved in the work. Gaussian from University of Western Ontario is doing a lot of interesting analysis right now. And also like to thank my wonderful advisors, Patrick and Jimmy, and for being so supportive throughout my PhD career. And also in all of the projects I've been involved. And if you are interested in details, hopefully we have a preprint ready soon, but you can take a look at the website now. And if you want to try it out on your own, BaseJP is the package, it's on Chrome. Okay, so that's all. Thank you.
We don't have too much time.
When you mentioned at the end that one could try splines and work out this approach through the spline approximation. So did you mean in the last picture that you actually tried and found it? Or?
Yes. Actually, we had all those technical details, but this is something already available even in the software. So the idea is that if you do a basis expansions of the functions and then you put this into like a set of conditions defined by a set of test functions in FEM, then you can turn these equations into some matrix form for the precision matrix of the weights. Yeah.
Okay, but the try it's reasonable.
Yes, it's reasonable. It's converged. You have some based on like existing result, you can easily prove some convergence rate as the number of basis groups if you place them equally. And also in practice, the convergence is quite reasonable. It's almost the same compared to the Markovian result, which is exact.
This study with splines was somewhere published, or is it only just?
It will be published together as part of this project, but the essence of this FEM approximation is already like well established in the Gaussian Markov random field approximation. So you can take a look at those two papers, which are very similar in the structure of the technique. This paper in 2008 was, I think, the first attempt trying finite element approximation to approximate a differential equation-based Gaussian process. And this paper, which is a bit more recent than us, also shows the technique involved.